Last class, we started looking at atomic spectra and the quantized model. We briefly read through the objectives and highlighted words that we were unfamiliar with. And then we moved on to different types of spectrum. So spectroscopy is used quite regularly to determine the type of element that is present, and we can even use this to determine what type of elements are present in our sun and stars, and from there we were actually able to deduce that they are made out of the same elements that we see here on Earth. So the three different types were continuous, where you can see all the different elements of a Roy G. Biv spectrum. And then there's emission, or a bright line spectrum, where you only see the visible bright light stripes, but still representing different frequencies of light. And then the last one is an absorption, dark line spectrum, and that's the opposite of it, where you see most of the Roy G. Biv, but then there's black strips representing missing frequencies. So today we're going to look at how that influenced the newest model and the one that we still use today about how a atom is composed. Before we do that, I just want to remind you that every element has a unique bright line and dark line spectrum, and the way that they match up looks like this. So this is a hydrogen absorption spectrum, and we have both the absorption spectrum here and we have the emission spectrum here. So you can see that they are lining up and missing the exact same wavelengths that they're showing on the other one. So that brings us right into Bohr's model of the atom. So Niels Bohr was actually working under Rutherford as kind of one of his helpers, and he also worked with Thomson for a brief period of time. So he was around a lot of different theories that were spiraling around at this point in history. So we've already looked at the two different models, both Thomson's and Rutherford's, but Bohr noticed that there were still flaws in these. And we talked about this last class. Essentially, if there are electrons orbiting a nucleus that are constantly accelerating, they should emit electromagnetic waves. And if this were the case, it would take energy from the electrons. As a result, the electrons would essentially decay in a short amount of time. And if this were the case, we would not have what we call stable matter. Everything would just constantly be decaying. So from there, they were able to, deduce that there's got to be something else that we are missing here. So he made a couple proposals, and like I said, a lot of these are things that we still continue to believe true to this day. The first thing that he proposed was that electron energy is quantized. And we've seen this before in terms of the elementary charge, but essentially only electrons with specific or exact amount of energy are allowed in each energy level. So we'll see the model of the electron that we're going to be looking at. And it's going to have the nucleus with kind of like orbits around, not exactly, but we'll get into that in a second, but essentially only electrons with specific energy, so like an exact amount, are allowed in each level. So each of the circles that I drew around the nucleus, those would be classified as a level. So even further than that, electron orbit levels are quantized. So there is a level 1, there is a level 2, and these occur at specific, once again, specific distances. So it's all very precise from the nucleus. And you can think of it as like they're only allowed in those specific distances. They can't go anywhere else. Oh, that didn't come up very well. Nucleus, there we go. Okay, and then the last one is that electrons exist in stationary states. So essentially, we have an atom has to be in its home state, and that's where it prefers to stay. If it's going to change states, energy is either going to be emitted or absorbed. So, and because it is in stationary state, this is why it doesn't emit EMR, which, if you remember, was the problems behind Rutherford's and Thomson's models. So, although he does state that it's not going to emit EMR, he doesn't exactly explain why. So Niels Bohr made a lot of really important contributions to the way that we look at an atom, and he was able to use spectroscopy to do that. So flipping back to spectroscopy for just a second here, a lot of the importance that Bohr was contributing with, it was the line spectrum. So essentially he noted that if energy is absorbed, then we are going to be moving an electron from the nucleus out to an outer level. It doesn't necessarily have to be a second level, it could be a third level, fourth level, but if this is the case, the electron, so let me scroll here, the electron is moving away from the nucleus. And as it does that, it takes in energy, it absorbs energy. And when it's moving towards the nucleus, then it is going to emit or release energy. So depending on which is happening, he was able to deduce that you find different absorption and emission spectrums. So if energy is going to be absorbed, and you'll see that here, then you are going to get an absorption. Spectrum. Makes sense. Absorption, absorbing energy. It's gaining energy, but it has to gain the exact amount of energy in order to move to a different energy level. And that goes back to what we were talking about before with the quantized levels. It needs to have an exact amount of energy to move to the other level. And then opposite of that, if energy is emitted or released, then we are going to have an emission spectrum. So he specified it looking at the hydrogen atom and spent a lot of time analyzing what different energy levels were available in a hydrogen atom. Later, they've been able to do more than the hydrogen atom. However, the hydrogen atom has a lot of specific calculations that pertain to it. We don't look at them in the scope of this course because they only pertain to the hydrogen atom. However, they were very useful formulas that they use in this day and age. So there are two different ways that an absorption spectrum can be made. We know that it has to gain a certain amount of energy to move to that outer level. So the first way that it can do this is when it is exposed to a photon that has that exact amount of energy needed to change the levels. And then the electron is going to absorb all the energy and transition to that next state. And then the second way would be that if it has a collision with a free electron, and the electron would absorb only the energy needed to transition. And the free electron keeps moving with any of the remaining kinetic energy. So either a collision with a free electron or exposed to a photon with the exact amount of energy, either of those will cause the electron to move to an outer energy level and emit a absorption spectrum. And then lastly, we have already talked briefly about this, but the emission spectrum, that's just going to be in order to go back to their stationary state, they will emit energy, and that is because typically electrons want to be in their stationary state, and it requires more energy for them to move to a different state. So they want to be in their home state, and if you want to think back to chemistry, think about they want to be in that cloud where they have pairs of electrons because they're more stable, and then the valence electrons, those are less stable. So if they're in their stationary state, they're the most happy with life and they are good at being there, but anything else requires energy. So as I mentioned before, there's quite a few different formulas that are in this area. However, in the scope of Physics 30, we're mainly going to be looking at these diagrams that display the movement from different levels. So essentially, you're going to have some kind of diagram that shows the different energy levels. So here we have ground state, then we have A. A lot of the times the name label it as 1, 2, 3, 4, 5. So, and a lot of times N is used to denote them. So level 1, 2, 3, N equals 1, N equals 5. So the question says the energies of an electron within an atom are most often given relative to the ionization shown below. So one thing that I want to state, just because sometimes the diploma questions are weird with the way they ask it, here it shows you where ionization is. If they don't show you where ionization just means that you are going to be losing the electron completely. So if it says you need to ionize the atom, it means you're losing the electron completely. In this diagram, they show you where that is, but you need to know that they might not show you where that is, and it just means get past that last level, in this case 5. So we're shown the different energy levels, and then it asks us to determine the frequency of a photon released as an electron makes a transition from D to B. So at this point, we need to learn a new formula. So our formula is just, well, it's not really new, but it's your change in energy is equal to, especially for this one, the absolute value of your final energy minus the absolute value of your initial energy. So just our final minus our initial, so not too new, but we do take the absolute value of it to show the change in energy rather than whether it's positive or negative. So in order to find the frequency, first we need to find the change in energy. I'm just going to zoom out here. Okay, so let's find the change in energy from D to B. So change in energy equals absolute value of EF minus EI. So we're going from D to B. So at B, which is our final, we have negative 10 electron volts. And at our initial, at D, we have minus 2 electron volts. So you can already see there that there's going to be a difference, even without typing that in your calculator. It's going to be a difference of 8 volts, 8 electron volts. However, if you do want to use your absolute value, grade 11, so that you really know what that is, we would have the absolute value of -8, so our answer would be 8 electron volts, although that's not our final answer. So from there, we need to find out our frequency. So we have the energy, and we still know Planck's constant, so from there we can manipulate the formula to get energy divided by Planck's constant. We can leave it in electron volts as long as we use that Planck's constant to give us our frequency. So frequency equals 8 electron volts divided by 4.14 times 10 to the power of -15 electron volts per second, times second. And that gives us a frequency of 1.93 times 10 to the 15th. So that photon with a frequency of 1.93 was able to cause the electron to jump from D to B. All right, let's try question B. Determine the number of photons of different wavelengths that could possibly be produced due to an electron at level C moving back to ground state. So let's go back to our diagram. We're at level C and we're wanting to move back to ground state. So there's three different things that could happen. You could go straight to A, and that's 1. Or you could go from C to B, and then from B to A. So in total, there are 3 different wavelengths that could be used. So we could go from C to A, from C to B, and from B to A. So therefore, 3 different wavelengths. And what that means is 3 different bands of light in order to get you to ground state. So the next page is a continuation of this example, and I've just reprinted the diagram for you there. Let's try the next question. An electron at ground state in the atom is struck by a passing electron. So here's that other thing that could happen, either free electron or photon, having an energy of 9 electron volts, and the atom's electron absorbs as much of the kinetic energy as possible. So remember, it takes as much as possible, and the rest stays with the free electron. So in this case, it says that it is at ground. So we're starting at ground with an electron, and it's hit with 9 electron volts. It can go from 14 to 10, that's 4, and to 7, that's 7, but it doesn't have enough energy to get to the next level. And this is where that quantized thing comes in. It can't make it to the next one, so therefore it's only going to go to C. So at C is where it'll stay, but it's only going to be absorbing 7 electron volts. So it will absorb as much as it can. Which is 7 electron volts. And then it also asks the kinetic energy of the passing electron after it collides. My pen's not working very well. So EK left will be the 9 electron volts that it started with, subtract how much it gave away to the electron in the atom. So the free electron will have 2 electron volts. Okay, and the last one for this example, minimum possible wavelength of light that could be released by the atom when the electron moves back to its stationary state. So we're continuing from C. We're saying that it went to C. So it went to C, and now it wants to go back to its ground state. So in order to find the wavelength, we are going to have to look. So first off, we're going from C to A. And we know that that is the change in energy is 7 electron volts. So then we just have to pick out a formula that's going to allow us to calculate the wavelength. So our formula E equals hc over lambda should do the trick. We can manipulate that to solve for energy, and from there make our substitutions. Okay, you can go ahead, pause the video, and do this yourself. There's the solution for you, 1.77 times 10 to the negative 7 meters. I want you to find out what type of EMR this might be. After you have done that, you can complete your turn, page 292, numbers 1 to 6,